So I needed to make a small announcement. Somebody pointed out to me that the quiz was due today, but because I have not completed 4 lectures, there's no point of having a quiz before the end of 4th lecture. So I've moved the deadlines for quiz 1 as well as assignment 1 to sometime in next week. So that way you will have ample time to complete the quiz as well as complete the assignment. The quiz is mostly based on lectures 1 to 4 stuff, so whatever we are doing right now. But a lot of it is prerequisite, so you should be able to do the quiz now if you feel confident. If not, then we'll of course go through lecture 1 to 4 and then you should be good for the quiz. Today the topic for discussion is, we'll start with our discussion on symmetric positive definite matrices. And then we'll talk about continuous functions, derivatives of differentiable functions, mean value theorem, Taylor series, and then convex functions and convex sets. So I'm not sure how much we'll be able to cover today, but if we cover everything, then that's great. If not, then we'll cover the spillover topics in the next class. Okay, so in the previous week or previous lecture, we were talking about positive definite matrices. So A is symmetric. So A is positive definite if and only if A is symmetric and X transpose AX is greater than 0 for all X in Rn minus the origin. And A is positive semi-definite if and only if A is symmetric and X transpose AX is greater than equal to 0 for all X in Rn. So there is a strict inequality here, and therefore we are removing origin. But here there is an inequality and origin is not removed. So that's the only difference. Right, so this is what we did in the previous lecture. Now I wanted to ask a question to this class. What is a special property of a symmetric matrix? So what do you think is something cool about symmetric matrices? And of course we are talking about it from the point of view of eigenvalues and eigenvectors. So does anything, when we talk about symmetric matrices, anything rings the bell from your linear algebra class? Yes.
The eigenvalues are all real.
Yeah. So if A is symmetric, then lambda i's are all real. So that's a very important result. I don't know, fact. It can be proven, but it's a very well-known fact. So you have a symmetric matrix, so A equals to A transpose. In that case, all the eigenvalues are going to be real. If you have non-symmetric matrices, sometimes the eigenvalues could have complex values. Okay, so but symmetric matrices, all eigenvalues are real. Anything else that you know about symmetric matrices in terms of eigenvectors? They are orthogonal. So V1 to Vn are all orthogonal. What that means is Vi transpose Vj equals to 0 for I not equals to j. So in 2 dimension, let's say A was a matrix in 2 cross 2 dimension and it is symmetric. Then in that case, this is my eigenvector like R2, this is my R2. And if you have one eigenvector like this, the other eigenvector will look something like this. So it's orthogonal to the first eigenvector. It's a very simple exercise in MATLAB to check. You can construct a symmetric matrix And then you check the eigenvectors and you do Vi transpose Vj for I not equal to j. And what you will find is that what is 0 in MATLAB? So can someone tell me what 0 in Python and MATLAB? So anything that looks like 10 raised to minus 10 or 10 raised to minus 15 is as good as 0, right? So you pick two eigenvectors of a symmetric matrix, you take the inner product in MATLAB, and you will find that either the value will be 0 or the value will be 10 raised to minus 15 or 10 raised to minus 16 or something like that. So that's as good as 0.
Can a non-symmetric matrix be also definite?
Sorry?
Non-symmetric matrix. Can a non-symmetric matrix be also definite?
No, non-symmetric matrices cannot be positive definite. So the definition of positive definite is it has to be symmetric and it has to satisfy this property. Okay? So symmetry is part of the definition of positive definiteness. So thankfully, if A is positive definite or positive semi-definite, it definitely has this property as well. So all the lambda i's will be real and the eigenvectors are going to be orthogonal to each other. But there is something more that happens in the case of positive definite and positive semi-definite matrices. So another fact, if A is positive definite, then lambda 1 to lambda n are strictly positive. If A is positive semi-definite, then lambda 1 to lambda n is going to be greater than equal to 0. Naturally, the eigenvectors will be orthogonal because it's a symmetric matrix. But the only other thing that gets added in the case of positive definite matrices is not just that lambda i's are real, but it's actually strictly positive. So you pick a symmetric matrix, you look at the eigenvalues. If all eigenvalues are strictly greater than 0, then you know for sure that it's a positive definite matrix. What's the simplest positive definite matrix? Identity matrix. Okay, so identity matrix is 1 1 1 1 1 along the diagonal, 0 along the non-diagonal entries. The eigenvalues are all the same. It's equal to 1. And what is the eigenvector? Remember, E1 and E2s are being used in this class to denote the unit vector in ith dimension. So E1 is 1 0 0 0 0, E2 is 0 1 0 0 0, E3 would be 0 0 1 0 0 0, and so on and so forth. Right? So this notation was introduced in the first class. EI is ith unit vector in Rn. So identity is a positive definite matrix. Identity is symmetric, yes. Are all eigenvalues strictly greater than 0? Yes. And eigenvectors are, of course, because it's symmetric, the eigenvectors are all orthogonal to each other. Perfect. Any questions so far? Yes.
When you said A bigger than 0, do you mean the determinant bigger than 0 also?
So this is a notation for saying that A is positive definite. So in this class, the notation for saying that something is positive definite is to write that the matrix is strictly greater than 0. Just in this class. It's not universally applicable, but in this particular, because we are going to use positive definite matrices a lot throughout the class, so this is how we'll denote positive definite matrices. Same thing, positive semi-definite will be denoted by this. Negative definite, we'll write it like this, and negative semi-definite matrices will be written as this. Okay, but we will not talk about negative definite and negative semi-definite matrices, but some people use it because they are doing research. But in this class, we will always be using these two notations. And I had also mentioned in the previous class that in some books, you will notice this this notation for positive semi-definite and positive definite. So this sign has some curve in it. So that's also sometimes in some books you will see that notation, and that also means the same thing. Okay, any other question? Awesome. Continuous functions. Okay, that's the next topic. I'm sure we all understand intuitively what continuous functions and discontinuous functions mean. Let me draw a function. So this is my x, this is my f of x. This is a continuous function. This is the discontinuous function. Okay, so in discontinuous function, the value here is going to be this value, and this one, this is just a way to show that this is sort of open in the sense that the function doesn't take this value, but it starts from here and goes all the way up. This definition is, there is no definition here. This is just a visual depiction of what a continuous and a discontinuous function looks like, but there are mathematical definitions of continuous functions. So let's look at what the definition is. And I'm going to cover two definitions, so that way you know what the different definitions are for continuous. They are all equivalent definitions. So one is the epsilon delta definition, which is f is continuous if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that fx minus fx prime is less than epsilon for every x prime such that x minus x prime is less than delta. This function f, I did not write it, but this function f is a function from Rn to R. How many of you have seen this definition before? Epsilon delta definition? Few people? Yes.
What's the word after the epsilon delta?
Definition. This is the epsilon delta definition. Okay. So f is continuous if for every epsilon greater than 0. Let's look at it in the picture. So here is my x. This is my f of x. This one. So I pick an epsilon greater than 0 and I look at this neighborhood around f of x. Okay, so this is the epsilon neighborhood of f of x, such that for all, and I can find a delta. So here is a delta around x, so that f of x minus f of x prime, so I pick any x prime within this delta neighborhood of x, and I know that f of x prime will also be close to f of x. Right? So this is true for every epsilon. So no matter how big or a small epsilon you pick, you will be able to find this delta neighborhood such that this condition holds. Okay, that makes it a continuous function. Yes, please.
Can you take the limit of the epsilon, like from the delta to 0 and the epsilon, the difference will also be 0?
That's right. That's exactly what will happen. But remember that here epsilon is a free parameter. You can pick epsilon the way you want to pick. Delta comes from the function itself. So delta is a function of what function you are picking, but this epsilon is a free parameter. You can pick epsilon as big or as small as you want. So you cannot vary delta. You can only vary epsilon out of your free will, and delta will change accordingly, depending on the function that you have picked. Okay, and this should be true for all x. This entire definition should be true for all x, in which case function f is continuous. The second definition is a sequential definition. F is continuous if and only if for every sequence xn that converges to x, f of xn converges to f of x, and this holds true for every x. So no matter how you pick your sequence that converges to x, your f of xn should also converge to f of x. Okay, this is a sequential definition. This is the epsilon delta definition. We are not going to be using this definition in the class too much, but this idea that if xn converges to x, then f of xn will also converge to f of x, this particular part is what will be useful for many results in the class. So if my solution is converging to a point, then I know that my function value will also converge to the function value at that point, because my function is going to be continuous. Okay, we are not going to talk about discontinuous functions in this class, but I still wanted to give you the definition so that we understand that for every sequence that converges to x, it doesn't matter how I construct that sequence, as long as it's converging to x, my function value will also converge to the function value at x. Okay, so this is the definition of continuity for functions that maps Euclidean space to real line. Let's look at the discontinuous function. Let's say I'm looking at this x and I'm picking a sequence which is coming from this side, right? So the function value is actually going in this direction, and the function value is going to converge to this number, but actually the function value at x is this number. Okay, so that's why I have constructed a sequence. So this has to be true for all sequence, right? But here, if I construct a sequence from this side, this condition holds, but if I construct a sequence from this side, this condition is not going to hold, as a result of which this function is not continuous. So as long as I can pick one sequence such that this condition does not hold, then function f is not continuous, which is what I have demonstrated there in that picture. Okay. Let's talk about differentiable functions. Now this is something that you may not have seen before, and the reason is generally in undergraduate classes people talk about functions of one variable, but here we are talking about functions of multiple variables. So this would be something new. So I have a function from Rn to R. When is this function differentiable? So if limit x plus delta ei minus f of x over delta, limit delta goes to 0, exists for all I and all x. So remember, this EI is the ith vector along in the Euclidean space, so ith vector where it's 0, 0, 1, 0, 0 kind of vector. So I add a small number delta to x, then I look at the difference, I divide it by delta, so I divided this difference by delta and I let delta go to 0. I want this particular limit to exist, in which case the function f is differentiable. Okay, you must have seen the definition in R to R. So in this case, function f is differentiable if limit delta goes to 0, fx plus delta over this exists. So this is the definition you have seen in the past when you were taking a course in calculus, probably in your second year of undergraduate. So this is the definition you are already familiar with. The only way I'm changing things here is now x is an Rn. So I need to check in every direction this condition should hold. So I'm just checking that along all the directions. So I have n different directions, or I want to make sure that in all n dimensions this particular condition holds, in which case the function f is differentiable. Any questions? Any heartburns with this definition? Okay, so all of us agree on this definition? The derivative of f will be denoted by this. So in the first few lectures, I'm going to write it as gradient of x of f. Okay, but in subsequent classes, I'll drop this x because I don't want to carry this x all over the place. So sometimes it's important to write it as derivative of x of f. Sometimes we won't write it, but anyways, this is how we will write it. And this is how the derivative is written as. This is a vector in Rn, and this is my gradient of xi of f evaluated at x. So this is the notation for derivative of a function with respect to x. Okay, so x is in Rn, x is in Rn. So I'm going to take the derivative of the function with respect to each of these x's. So x1, x2, all the way up to xn. Each of this number is going to be a real number, right? So this is a real number, this is a real number. I'm dividing it by a real number. I'm letting this delta go to 0. So what I get is a real number here. So each of these derivative of f with respect to xi is a real number. So I get a real number, real number, real number all the way up to here. So I get a vector in Rn. So you have a function that maps Rn to R. So that maps a Euclidean space to R. The derivative actually lies in Rn. Okay? So the derivative is no longer a real number, it's actually a vector. Okay? So that's where from now on in this particular class we'll always think of derivative as a vector. We'll never think of derivative as a scalar. Okay? So far you are all used to seeing derivative as a scalar. No longer that is going to be the case in this class. Awesome. So I talked about the first derivative. What about the second derivative, right? So you guys have studied that I look at the derivative of the function and I take the derivative of the first derivative of the function, I get the second derivative of the function. So let's look at what the second derivative of this function looks like. Here is the problem. The problem is if I want to take the derivative of this function again, I am now taking the derivative of a function that maps Rn to Rn, right? So the first derivative of the function takes as input a vector and outputs another vector. What is the derivative of a vector valued function? So this is a vector valued function. Okay? Let's think about it. So I have a function g that maps Rn to Rm. Let's try to be a bit innovative. Let's assume that this function is smooth, nice, continuous, smooth. Smooth means infinitely differentiable and all that, so I can differentiate this function. Let me write this g in a somewhat disaggregated fashion. So this is a disaggregated g. So this g was mapping Rn to Rm. I am now going to convert this complicated function into a function into real valued function. So this g1 is a function from Rn to R, and gm is a function from Rn to R. This is a function that we know how to differentiate. Right? So this is a function I know how to differentiate. But I want to differentiate this function. I need to do something about it. What would you do? So you went to Amazon, your Amazon boss tells you that we need to differentiate this function. What's going to be your solution? It's a $1 million job, okay? So you have to come up with an answer. You can't say, I don't know. So here is the convention. The derivative of g with respect to x is derivative of g1 with respect to x, and I'm going to stack it as a vector in a matrix. And what I get is a matrix. So I know how to differentiate g1, I know how to differentiate g2, I know how to differentiate gm. So I get n-dimensional vector here, n-dimensional vector here, and there are m such columns. So I get a matrix in n cross m dimensions. So it has n rows and m columns, right? So these are the m columns, and each of this vector has n rows, so we get a matrix. Let's look at an example, okay? So I'll let you write it and then we'll look at an example. Where should I? So let's say g is a function from R3 to R2. So I need a function log of x1 plus x2 square plus exponential of x3 and x1 cube plus x2 square root plus x3 raised to 4. Well, this is not defined for negative values of x1, so I need to maybe change these two functions. Can someone give me a differentiable function which is defined on negative as well as positive values? Let's say x1, x3 and x2 square x1, whatever. Okay, so now we get function that is defined over the entire Euclidean space R3, and I'm getting a two-dimensional vector as an output. Okay, so each of this is a scalar quantity, so I get a vector quantity, so this is in R2. So I'm going to call this as G1. This is my G1 and this is going to be my G2. So now I need to differentiate G with respect to x. So I need to differentiate this with respect to x1 first. So what's the derivative of this with respect to x1? x3. What about derivative of g1 with respect to x2? So I have to differentiate this with respect to x2. What about derivative of this with respect to x3? Now I have to differentiate g2 with respect to x1, x2 and x3. Sorry?
Plus x1.
Plus x1. Because there is.
Oh, of course. Yeah, thank you. Yes, thank you. So this is x1 plus exponential of x3. What about g2, derivative of g2 with respect to x1? So I have 3x1 square plus x2 square. What about derivative of g2 with respect to x2? So I have 2x1 x2 and derivative of g2 with respect to x3. x3 cube, right? Okay. So I get the derivative of g with respect to x. It's a matrix. It has 3 rows and 2 columns. Okay. Wonderful. So I have a function f. I figured out how to take the derivative of f. Now I realize that okay, I need to take derivative of a function that outputs a vector. So I disaggregated the function. Then I defined the derivative in this fashion. which allowed us to keep our jobs at Amazon, the $1 million job at Amazon. Okay, and now we have figured out how to differentiate a function that outputs a vector. How do we differentiate that function with respect to the input vector? So this is the way to differentiate the function. So let's go back to this example. So I have the derivative of function that takes as input Rn, outputs a vector Rn. I want to differentiate it again, right? So I want to differentiate it again. What will I get? It takes as input Rn and it outputs Rn cross n. Okay. So let's look at it again. So what's the second derivative of f? So again, second derivative, I'll have to write it as 2x's here because it's the second derivative. This is okay, so this was my function. So I have disaggregated this function into n different real valued function. Now I take the derivative with respect to x of these n different functions. I get a matrix, n cross n matrix. Let's disaggregate each of these terms. So what's the gradient of x of gradient of x1 of f? This is this is what the derivative looks like. So this is the partial derivative with respect to x1 and then partial derivative with respect to x1. This is partial derivative of f with respect to x1 and then partial derivative with respect to x2 and so on and so forth. Okay, so this term is going to be del 2f over del x1, del x2 and so on and so forth. Okay, so this is what this is going to look like. What do you notice about this matrix, second derivative matrix? This is my second derivative matrix. So I have a function of n variables. I take the partial derivative with respect to x1 twice. Then I take partial derivative with respect to x1 and x2. I construct this part of the column. Then I do the same thing, but here I have to take the partial derivative with respect to x2 and then partial derivative with respect to x1. And then I have to continue doing that operation for all the entries of the matrix. Okay, so I have n cross n computations to be done here. Anything peculiar about this matrix that you notice? Yes.
Symmetric,
Why is it symmetric?
because entry, the ij entry is equal to the j entry.
So you're saying that whether I differentiate a function with respect to x2 and then I differentiate with respect to x1, it's the same thing as differentiating with respect to x1 and then differentiating with respect to x2? Yes, so that is exactly the case. So if you have differentiable function, a nice function of multiple dimension, it doesn't matter in what order you are doing the differentiation, you will get the same number. So this number where you are differentiating with respect to x1 and then you differentiate with respect to x2, it's actually going to be the same as the number you get when you differentiate with respect to x2 first and then differentiate with respect to x1. Okay, we can see that in this particular example. Let's pick some function. Let's say x2 square x1. Okay, so I have x2 square x1. Let's take the derivative with respect to x1 first and then derivative with respect to x2. What do I get? What is the derivative with respect to x1? I have x2 square and this is 2x2, right? Let us change the order of the differentiation. What do I get? Del over del x1, x2, no, it's not x2 square. Oh, I'm differentiating with respect to x2, so I get x1, 2x1 x2, and this is 2x2. So I get the same derivative. So no matter in what order I did the differentiation, I get the same derivative. So this matrix is actually symmetric, as a result of which you don't have to perform n square computation. You only have to perform n square over 2 computation. Okay, so you don't have to look at any of these matrices. You just compute the upper triangular terms and then you copy and paste it in the lower triangular terms. So it's actually a symmetric matrix. So what happens to the eigenvalues of this matrix? It's always going to be real. What happens to the eigenvectors of this matrix? It's always going to be orthogonal. No matter what differentiable function you pick, you take the second derivative of that differentiable function, your eigenvalues are always going to be real numbers. Your eigenvectors are going to be orthogonal to each other. Okay? So that's the realm in which we will be working in this entire class. Knowing well that a lot of interesting optimization problems will be for functions that cannot be differentiated. Okay? We won't cover that in this class, but people in industrial engineering department worry about those problems all the time. Okay? Awesome. Any questions so far? So that's a lot of derivatives in a single class, but we won't have this again. This is your chance for asking questions. Okay, so what we did, I have a function, I differentiated it, I get a vector. I differentiated it again, I get a symmetric matrix, and therefore all the different properties of symmetric matrix kicks in at that point of time. How many of you have read the news about transformers? I mean, not the news, but I'm assuming everybody knows about transformers, ChatGPT, and so on. What is the dimension n in transformers? When you're doing the optimization, when you're training neural network or transformer network for training, let's say, ChatGPT, what is this n?
Too big.
How big?
Maybe millions or something.
So the latest models are being trained with what they call 600 billion parameters or 800 billion parameters. So this n is 800 billion. When they are training it, they are computing this. So they are differentiating a function, and this vector is a 8 billion or 800 billion dimensional vector. And then they are doing the training. So we'll talk a lot about those things towards later classes, but I just want to give you an idea of what this vector might mean in different contexts. Okay, so if I'm running a vehicle, what are the things that I control in the vehicle? I control the brake and I control the accelerator. Those are the only two things I control. If you have a hybrid vehicle, then you tend to also control the power split. Okay, so there is another ratio that you also tend to, we don't control it, but the engine has to control it, okay, to figure out how much energy needs to go back into the battery versus how much energy should be spent on propelling the vehicle. Gear, most of the cars are automatic now, but I don't know how many of you drive manual vehicles? Oh, wow. That's the largest number of manual vehicle drivers I've had in my class before. So anyways, good. So I guess some people are into gear optimization stuff, but so gear, by the way, gear, does it take value in Rn? No, it's actually a discrete variable, 1 to 6. So in those cases, there is no notion of differentiation, right? So if you were to optimize a vehicle, and you have 2 or 3 different parameters that you are optimizing, all of which are real numbers, so you are taking the derivative only in 3 dimensions. Okay, so there you will be taking the derivative in 3 dimensions. If you want to be more fancy, you can take the second derivative, in which case you will be computing 6 or so different derivatives. If you add gear to that particular mix, so you have 4 dimensions, but the 4th variable is actually a discrete variable, then you get into a lot of trouble with respect to the optimization that we will study in this class. But there are ways to solve those kind of problems as well, which we will not cover in this class at all. Okay. So this class will look at nice functions, which is useful in automatic vehicles, but we will not look at bad functions which are useful in manual vehicles. But you are solving that problem in your head all the time. You're optimizing in your head which gear to pick all the time. Okay, right? So while driving the vehicle, you are taking derivatives and you're getting vectors in R3. When you are training large language models, you're computing vectors in R raised to 8 billion, right? If you're training a small image net or something, which is what Google does when it sorts the photo and figures out who's there in which picture. If you have an Android phone and you take a picture and you put it on Google Photos, it does all that sorting. And in those cases, you are looking at neural networks with maybe a few million, like 6 or 7 million, something like that, parameters. So there you are taking derivatives that have dimensions of the order of 7-8 million dimensions. So really, it's very problem dependent. It's dependent on the situation. And different optimization problems will have different dimensions, and you will have to compute all these derivatives. Okay. Okay. We have 5 more minutes, so I'll talk a little bit about some important results in this. So mean value theorem. So these are the theorems that you might have studied in your undergraduate calculus class. So for every x, for every d, there exists alpha greater than 0 such that f of x plus d equals to f of x plus gradient f of x plus alpha d transpose d. So for every x, for every d, there exists alpha greater than 0, such that this equality holds. Taylor series f of x plus d
Second term, x plus alpha d or just for
alpha d, yeah, x plus alpha d. So I'm going to take a step in the direction of d. So I'm standing at x. I want to find out what the function value at x plus d is. There exists an alpha greater than 0 such that I take a small step in the direction of d. I look at the derivative of the function at that point, and then I take an inner product with d, and I get an equality here. Okay. This is the famous Taylor series expansion. Fx plus d is fx plus gradient of fx transpose d plus 1 over 2 factorial d transpose second derivative d plus higher order terms. Okay. We generally will not care about higher order terms, and the way we will denote this will be small o of norm of d square. Okay, that's how we'll denote this higher order terms. Have you seen Taylor series for functions of single variables before? Right? Everybody would have seen that. Mean value theorem for functions of single variables. So this is just a multidimensional extension to those results that you have already seen in the single dimensional case. Okay, so that brings me to the end of this particular lecture. I think in the next class we'll start a new topic, which is convex set and convex function, after which we'll jump into optimization. Okay, so then we'll be done with all the prerequisites. Thank you, and see you on Friday.
Trying to remember.